Today, we'll be discussing eigenvalues, eigenvectors, what they are, why they're important, and how we can figure them out. Hello, welcome back to the Quant Plus YouTube channel. Today, we're going to be discussing eigenvalues, eigenvectors, and their applications, as well as an intuitive explanation as to why we calculate them the way we do. So to begin, we have this relationship, where A is some matrix, V is some vector, and lambda is a scalar. And what this formula is, what the relationship that this formula is representing is that by multiplying the vector v by some matrix A, we get lambda times v, where lambda is some scalar value. If lambda is positive, then we have a scaling of the original vector, and it maintains the same direction. If lambda is negative, then we have a scaling potentially of the vector v, as well as going in the exact opposite direction. And more generally, we can think about transformations, especially linear transformations, as being modeled by multiplying by a vector, right? So this is an equivalent statement to saying t of v is lambda times v, where the transformation t is accomplished by multiplying by the matrix A. This is an important concept in many mathematical fields, and one pretty important and common application of this idea is in principal component analysis, where this directly plays into how the components are calculated and essentially the weighting of each component. Well, with this idea out of the way, if you've seen this concept in your linear algebra class, you have very likely seen this formula. The determinant of A minus lambda I is equal to 0. And then from here, we would want to solve for lambda. Intuitively, if we start with the definition, why does this make sense? Let's see. If we start with our definition of A times V is lambda times V, by left multiplying both sides by the identity matrix, then ultimately we change nothing, right? This is allowed by the rules of matrix algebra. Well, I times A, where I is your identity matrix, didn't really change anything, right? We still have the matrix A. However, on the right side, if we do a bit of cleanup, then we get to a matrix multiplication, and that will help us in 1 second. So reordering the right side so that it makes it more sense, because it doesn't really make sense to have a matrix multiplied by a scalar. Instead, it should be a scalar multiplied by a matrix. We get to the following location. Then, by moving terms to one side, like this, we get to this location. And then, considering that the vector v is essentially a common factor, we can rewrite this like this. I made a little bit of a mistake. Let's clean this up. Equals the zero matrix, the zero vector. And the final transformation is A minus lambda I times some vector v is equal to the zero vector. We are going to assume that v does not equal the zero vector, because if v is indeed equal to the zero vector, then anything times the zero vector is the zero vector, and we don't have a unique value that maintains this kind of relationship. So the vector v, we're assuming, does not equal the zero vector. Consider that this is essentially a system of equations, and for the sake of simplicity, if we consider the 2 by 2 case, then as a reminder, we're going to define A as following. A is going to be this matrix. Our 2 by 2 identity matrix is this one. And we're going to define V like this. From here, we can see that A minus lambda I is as follows. We have the vector, the matrix A minus lambda times the identity matrix. And when we add matrices, right, this is done component-wise. So the resulting matrix is A minus lambda, C, B, and D minus lambda. Then, writing out this relationship right here, we get that A minus lambda I is the matrix that we just calculated, times the vector V. Oh, I made another silly error. This should be this one where the vector V is non-zero. Is equal to the zero vector. And from here, we can treat this like a system of equations because that's exactly what it is. I'm going to write the augmented matrix out. And apply the techniques of row reduction to solve the system, right? Where now A minus lambda I is essentially our coefficient matrix, and the 0, 0 vector is our solution vector, right? So applying the techniques of row reduction, the first thing I'm going to do is divide the first row by A minus lambda to get this. And then I want to get rid of this C, right? Because I want it to be in row reduced form. So I want it to be like this. And to achieve this, I have to multiply the first row by C and subtract that result away from our second row. So what we end up with is D minus lambda minus B over A minus lambda. And we still have our zeros. By creating a common denominator in the bottom right entry, we get to here. I just noticed that I forgot to write out the multiplication by C on the B over A minus lambda term. And in the final step of row reduction, we can get rid of the B over A minus lambda term, and what we get is this. Well, notice how this entry in the bottom right corner is very, very, very reminiscent of what you would get by finding the determinant of A minus lambda. So if we consider setting it equal to 0 like this, and solving, or at least rewriting, we can, in the first step, we would multiply both sides by A minus lambda, resulting in this relationship here. Well, this is exactly what you would get by finding the determinant of a minus lambda I and setting that equal to 0. So as a reminder, if we define a minus lambda I, or at least we solve for a minus lambda I, and we get this matrix here, then applying the standard way of calculating a determinant, or a 2 by 2 determinant, I should say, then the determinant of a minus lambda I is the determinant of this matrix, and we're going to multiply along the diagonal and subtract away the result off the diagonal, getting us to a minus lambda times d minus lambda minus bc. And by our formula at the very top, we said that this should equal to 0. If this indeed equals to 0, that's exactly the relationship we found through the row reduction calculation. And this is an intuitive, or at least more intuitive, explanation as to why we find eigenvalues by solving this equation, which is often referred to as your characteristic equation. Well, now that we know we have a formula and an intuitive explanation as to why it works for finding eigenvalues, what are eigenvectors? Eigenvectors are the vectors corresponding to the given eigenvalues. So, for example, if we find that lambda is equal to 2, then we would say A times our vector v is lambda times our same vector v, and this relationship becomes A times the vector v is 2 times our vector v, because we just solved that lambda is equal to 2 in this particular example. From here, we can solve for the components of the vector v and determine our result. So, if you found this content informative or interesting in any other way, please support the channel by sharing this video with your network, liking the video, and subscribing to the channel. If you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great evening.